It feels like every time I check the news, bam, there's some crazy new tech thing, a gadget I've never heard of, software that's smarter than me.
Yeah.
It's insane. Like, when will it end? Is this constant tech evolution a new thing?
Well, it's actually kind of fascinating how often we see the same feeling of rapid transformation throughout history. These periods of incredible technological change aren't isolated events. They sort of build on each other, creating this foundation for the world we have now.
So we're not unique in feeling overwhelmed by the pace of change.
Exactly. It's a recurring theme.
Okay, so for this deep dive, we're going deep into, well, exactly the history of these shifts. We've got some amazing material to work with, including parts of the Dream Machine, which is like a fantastic look at the minds and ideas that sparked the information revolution.
It's an excellent source.
Really insightful. What we want to do today is map out those key periods of technological change and, go beyond just listing the events. We want to explore the how. How did these events shape technology? And how did that, in turn, reshape us, our society, our culture?
That's a great way to frame it. It's about understanding the ripple effects.
Exactly. Consider this deep dive your crash course in the history of the digital age. And hopefully it'll equip you to, better understand the tech landscape we're all navigating today.
It's not just about looking back. It's about looking forward with a more informed perspective.
Okay, where do we even start with something this massive? It's a bit daunting, to be honest.
Well, a good place to begin is actually before electronic computers even existed. We can look at the early seeds of automation. A figure like Vannevar Bush is a perfect example. The sources paint him as this incredibly hands-on innovator, someone who could think with his hands as well as with his brain. He was completely fascinated by what he called analogy machines.
Analogy machines. That's interesting. What exactly were those?
Imagine devices that used physical principles, gears, levers, even things like fluid dynamics to model and solve complex mathematical problems. Bush's differential analyzer is a classic example. But it could take weeks to complete a single complex calculation. And this really highlights the revolutionary leap in speed and efficiency that electronic computing would bring. It totally changed the pace of scientific discovery.
Right, the differential analyzer. The source material describes it as this massive contraption, almost like a giant clockwork brain. And it really did have an impact across various scientific fields, right?
Oh, absolutely. It found uses in electrical engineering, atomic physics, seismology, astrophysics. There's this example in the text that talks about calculating the trajectory of cosmic rays. It took something like 30 days and required multiple people working on the machine constantly. Just imagine the sheer effort involved in complex calculations before electronic computers.
30 days. Wow. And the text introduces Norbert Wiener during this period, right?
Yes. He was a brilliant mathematician. Like Bush, he was also intrigued by the possibilities of automated calculation. They formed this close intellectual partnership, despite coming from different backgrounds. Bush was an engineer, and Wiener was a mathematician, and their collaborations had a pretty big impact on the field.
Okay, so we've got those early attempts at automation. What comes next?
World War II really pushed things forward. We see the dawn of electronic computing. See, those earlier mechanical devices, even the electromechanical ones, had some major limitations. You had to constantly supervise them, and they weren't programmable in the way we think about it now, so there was a real need for something totally different.
Something faster and more autonomous.
Exactly. And that's where figures like George Stibitz at Bell Labs come in.
Okay, let's talk about him.
Stibitz's work was truly groundbreaking. He focused on using binary circuits to perform the most basic arithmetic operations: addition, subtraction, multiplication, division. But what's really insightful is his early concept for a user interface, one that could translate between our decimal system, the one we use every day, and the binary code that the machines understand. He was bridging the gap between human language and machine language, even way back then.
But the source material emphasizes that his complex computer, which is an awesome name, by the way.
Yeah.
It wasn't actually programmable in the modern sense. It also didn't have internal memory, so it was more like, as you said before, a super advanced calculator. Is that right?
Yes. It could handle specific tasks automatically, but to make it do something totally new, you'd have to physically rewire its circuits.
Got it. And then we have John Atanasoff and the ABC computer.
Mm-hmm.
Now, this is described as the first demonstration of a fully electronic computer.
It was a huge leap forward. The ABC used vacuum tubes for computation, a big change from the electromechanical relays used in older machines. Atanesov didn't get to develop it further, though, because, well, the war effort pulled him in a different direction. But the ABC served as a really crucial proof of concept, demonstrating the potential of electronics in computing.
And then comes Howard Aiken and the Harvard Mark I, also called the automatic sequence controlled calculator. It sounds impressive.
Yeah. Oh, it was. It was massive, 8 feet tall and 51 feet long. And this guy, Thomas Watson from IBM, he really understood PR, so he insisted on this futuristic casing for the Mark I. Stainless steel and glass. The whole thing looked like it came straight out of a science fiction movie.
It definitely captured the public imagination, didn't it?
Absolutely. And it led to people calling these machines electronic brains. Although Aiken himself, he didn't really like that term. The text also hints at some tension between Aiken and IBM.
It sounds like there were some big personalities involved.
Definitely. Aiken wasn't always thrilled with how much emphasis was placed on IBM's role in the project, and it seems like that rubbed Watson the wrong way. But regardless, the Mark I was a huge step forward. It really showed the world the potential of these machines.
And then there's John Mauchly, J. Presper Eckert, and their creation, the ENAS. The sheer scale of that project is mind-boggling.
It really is. Think about it. Built under immense wartime pressure, the ENIS was huge. It occupied an entire room, weighed 30 tons, and had over 17,000 vacuum tubes. The source material mentions that there were billions of opportunities for failure every second because of the sheer number of components.
Billions. And they actually got it to work.
That's incredible.
So these early electronic computers were much faster than anything before them, but they still needed a lot of manual intervention, didn't they? What was the breakthrough that finally moved us towards the computers we use today?
That would be the stored program concept. This idea completely revolutionized computing. Instead of just focusing on building faster hardware, people started thinking about making the machine itself more autonomous, more flexible.
Okay, that makes sense. And this idea really started to take shape with the EDVAC project, right? And John von Neumann's role in all this is crucial.
Absolutely. His report on EDVAC focused on the logical structure of a computer, the architecture, not just the specific hardware, which, as we've seen, was changing so rapidly back then. His report emphasized this revolutionary idea, storing the program instructions in the computer's memory, along with the data it was working on.
So instead of rewiring the entire machine for each new task, you could just load a new set of instructions.
Exactly. And that's how we do it today. That idea led to a huge increase in flexibility and automation. But it wasn't all smooth sailing. Eckert and Mauchly, they had their own ideas about the stored program concept, and there were some disagreements about who deserved credit. They even ended up in a patent dispute with von Neumann and the University of Pennsylvania. It goes to show that intellectual property was a big deal even in those early days.
So even with these amazing advancements, there were still a lot of growing pains. But the stored program concept, it was a fundamental change. It laid the foundation for everything that came after.
Absolutely. It enabled the software-driven world that we live in now.
Okay, we've gone from mechanical to electronic, and now, thanks to the stored program concept, to programmable machines. What's next in this technological evolution?
Well, in the 1950s and 60s, we see the rise of interactive computing and time sharing. Back then, using a computer was often a batch processing affair. You'd submit your program, input your data, and then wait. Sometimes hours, sometimes days for the results. But J.C.R. Licklider, he had a different vision, a much more immediate way for people to interact with computers.
Licklider. The source material calls him computing's Johnny Appleseed, which is quite a title. Why was he so influential?
He had this incredibly forward-thinking view. He talked about human-computer symbiosis, where humans and computers would work together in a much more closely integrated, interactive way. He also imagined computers as communication devices, and even this concept he called the intergalactic network.
That sounds strangely familiar.
It does, doesn't it? His ideas really foreshadowed the internet we have today. He really understood the potential of computers for communication and collaboration, even decades before it became a reality.
His vision was truly ahead of its time, and Project MT at MIT was a major real-world experiment in bringing that vision, that interactive computing, to life through time sharing.
Right. Time sharing was this ingenious idea. You have one powerful central computer, and it rapidly switches its processing time between multiple users, each at their own remote terminal. It basically created the illusion that each person had their own dedicated machine.
Like a virtual computer for everyone.
Exactly. And this was really important because back then, computers were expensive.
Yeah.
Time-sharing democratized access to computing power. It also fundamentally changed how people interacted with computers. It was no longer this passive, batch-oriented process. It became a much more active back-and-forth exchange.
And Project Emmet didn't just change how people used computers, did it? It also led to some interesting social developments.
Yes, this experiment in shared computing, it kind of accidentally gave rise to online communities. People started using rudimentary bulletin boards, early forms of email, even sharing software.
So they were already sharing and collaborating online.
Yes, and they even called it freeware. It's amazing to see how these early online interactions foreshadowed so much of what we see on the internet today. These weren't just tools for calculation, they were becoming platforms for social connection and information exchange.
It's like they were building a prototype for the digital world we know now. And it's interesting to contrast Licklider's vision of this interactive future with the prevailing, batch processing approach. The text mentions John McCarthy's growing frustration with those limitations.
Yeah, McCarthy was all about a more responsive interaction with computers, especially for fields like artificial intelligence, where you need that quick feedback loop, to explore and experiment. He felt that the slow turnaround times of batch processing were a major roadblock.
And on the topic of artificial intelligence, the Dartmouth Summer Research Project in 1956, which McCarthy helped organize, it was a really significant event, wasn't it? It really solidified the idea of using computation to model and understand human thought.
Absolutely. That project, along with the logic theory machine developed by Alan Newell and Herbert Simon, was a turning point. They wanted to show that computation was, at its core, the analytical language for understanding how we think. And their success in using the logic theory machine to automatically prove mathematical theorems was huge. It really suggested that machines could, in fact, exhibit intelligent behavior.
Okay, so a lot was happening in this era. We also saw the emergence of the first interactive computers built with transistors, a major upgrade in technology. And of course, the founding of Digital Equipment Corporation, BEC, by Ken Olsen and Harlan Anderson.
Right, and it's interesting that Wall Street wasn't initially very enthusiastic about their venture.
Really? Why not?
Well, there was a lot of skepticism towards high-tech startups back then, but DEC's focus on interactive, smaller, and more affordable computers turned out to be a brilliant move. There was a growing demand for more accessible computing power, and they were in the perfect position to meet that demand.
They were ahead of the curve.
They were. And then there's the development of CTSS at MIT, the compatible time-sharing system. Developed under the guidance of Fernando Corbato, it was one of the first working examples of time-sharing. Of course, there were technical hurdles. It was a brand new concept, but they got it working.
CTSS was really important, wasn't it? It proved that time-sharing could work on a larger scale.
It did, and it laid the groundwork for more sophisticated multi-user operating systems. The text tells this funny story about Joe Weizenbaum. He was an early user of CTSS, and he got super frustrated with the system. It's a reminder that as interactive computing started to move beyond the research labs, people's expectations for reliability and responsiveness really started to grow.
Right, and they wanted it to just work.
Exactly. And another interesting thing about CTSS is that users started writing and sharing their own commands, which, when you think about it, that's like the very beginning of a software industry. People were already collaborating and building on each other's work.
The collaborative spirit of the internet was there from the start.
It really was. And Corbato, he understood how important trust and reliability were going to be in these shared systems. That was a key insight.
Okay, so we've seen computing become more interactive, more accessible. What's the next big shift?
Well, the next big idea was networked computing. Licklider's 1963 memo about his intergalactic computer network, it was mainly focused on his community of ARPA-funded researchers. But the underlying idea was huge connecting computers across vast distances to enable collaboration and resource sharing.
The challenge, as the text points out, was figuring out how to actually do it. How to overcome the geographical barriers and allow researchers to easily exchange programs, data, everything.
Right. And Licklider and Robert Taylor, who had joined his group at ARPA, they were both passionate about human-computer symbiosis, and they saw networking as a crucial part of making that happen. Taylor was instrumental in securing funding and support for these early networking efforts, including the work of Douglas Engelbart, who was doing some truly groundbreaking stuff, and of course the continued development of Project MC.
And this is where we see the development of the ARPANET, right?
Mm-hmm.
And this revolutionary concept of packet switching in the late 1960s.
Exactly. Larry Roberts, he was the driving force behind the ARPANET. Packet switching was a radical idea. It was a completely different way of thinking about data transmission.
Okay, so how does it work? Explain it like I'm, well, not an expert.
Instead of setting up a dedicated, fixed connection for every single communication, they broke the data down into small packets. These packets could travel along different routes across the network and be reassembled at the destination.
So it's like sending a letter by cutting it up into pieces and sending each piece separately and then putting it all back together at the other end.
Yes, a great analogy. And this made the network more efficient and much more resilient. Because if one path was congested or down, the packets could just take a different route. But of course, there was pushback. People within the research community weren't so sure about this newfangled approach.
They were probably comfortable with the way things were.
People often are. But some key figures really embraced the idea. Douglas Engelbart was a huge supporter. He saw the ARPANET as a platform for what he called groupware collaborative work. And he was a big advocate for the Network Information Center, a hub to support this emerging network.
And it's worth pointing out that this wasn't just an American effort. Roger Scantlebury, over in the UK, was independently working on very similar ideas around packet switching at the same time.
Absolutely. He was working at the National Physical Laboratory, and his ideas were very similar to Robert's plans for the ARPANET. It's amazing how parallel innovation was happening across the world. And we should also mention Paul Barron at RAND. He had explored similar ideas even earlier. He was looking for ways to build a communication network that could survive a nuclear attack.
So the focus was on resilience and reliability.
Exactly. And even though his motivations were different, his work shared that core idea of breaking data into packets. And when the ARPANET launched, with those first 4 nodes connecting universities and research institutions, it marked a huge step towards making networked computing a reality.
It was the beginning of something truly transformative.
It was. And Len Kleinrock at UCLA, he insisted on having network measurement software built into the system from day one. UCLA became the Network Measurement Center, gathering data on how the network was actually performing. And this was crucial for identifying problems and making improvements.
It sounds like a lot of trial and error.
Oh, it was. Steve Crocker, one of the early pioneers, talks about the challenges of creating the protocols, the rules that allowed these different systems to communicate with each other. It was a constant process of experimentation and refinement, but they were building something truly revolutionary.
Okay, we have these interconnected networks starting to take shape. What's next in this story?
The next major shift is the beginning of the personal computer revolution. In the mid-1970s, most people were still focused on those large, centralized time-sharing systems. But something new was brewing. Fueled by the earlier ideas about interactive computing from MIT and this growing hobbyist movement, people started thinking about personal computers. Computers that individuals could own and control.
Like a computer for everyone.
Yes. And the Altair 8800, even though it was initially a do-it-yourself kit for hobbyists, it was a pivotal moment. They couldn't believe how many orders they got. It showed that there was a huge demand for personal computing power, way beyond what anyone had anticipated.
It tapped into this desire for individual empowerment, didn't it?
It did. And Gary Kildall's CP/M operating system was also crucial. It created this separation between the hardware and the software, which allowed for a lot more flexibility and made these early personal computers more user-friendly.
So software was becoming its own thing.
It was. And then there's Xerox PREC. They were doing amazing things. They developed these incredibly advanced personal computers like the Alto, which had a bitmap display and a graphical user interface.
That sounds familiar.
It should. It's basically what we all use today. But back then, some people within Xerox, they saw these personal computers as interesting, but not necessarily the future of computing. They were so used to the idea of these big, centralized machines. It's hard to believe now, but it just shows how difficult it can be to predict how a new technology will change things.
It's amazing that they almost missed the significance of their own invention.
It is. But Bob Taylor, he was a big believer in the bitmap display. He saw the potential for a much more intuitive and visually rich user experience. And Bob Metcalfe's development of Ethernet at PARC, that was also huge. It provided the foundation for local area networking, allowing these personal computers to connect and share resources.
So while PARC was focused on local networking, Vint Cerf and Bob Kahn were working on something much bigger. They were developing TCP/IP, the set of protocols that would form the backbone of the internet.
That's right. It became clear that these different independent networks, they needed a way to talk to each other. And TCP/IP was the solution. It's like a universal language for computers. And it's worth mentioning that Bob Metcalfe at Park, he had also been exploring similar ideas with his PUP, which stood for PARG's Universal Packet.
So many ideas swirling around at the same time.
A real melting pot of innovation.
Okay, so we're in the late 70s and early 80s now. Personal computers are starting to move from hobbyist toys to something much more serious. And the ARPANET is evolving. The Unix operating system is becoming popular, especially in academia and research. And we're seeing these early online communities like Usenet start to flourish. It's like Licklider and Taylor's vision of computer-mediated communication was starting to come true.
Yes, and Unix was a big part of that. It was incredibly portable because of the C programming language developed by Dennis Ritchie, and that portability helped it spread quickly. And Usenet, well, it showed the power of online communities, people forming connections based on shared interests. It really foreshadowed the social media platforms we have today.
It's amazing to think that the basic building blocks of today's digital world were being laid down decades ago. And it's interesting to see how different companies reacted to these changes. The text mentions DEC's initial hesitation to embrace personal computers. They had the technology, but didn't fully commit to it.
Right. But at the same time, Hewlett-Packard, they were having success with their programmable pocket calculators. They were marketing them as personal computers. It just goes to show how different companies had different visions for the future.
And as we reach the latter part of this period, the text brings us back to Licklider. His warning from 1979 about the danger of fragmented and potentially oppressive information systems if we don't actively work towards an open, universally accessible multi-net feels so relevant today.
It does, doesn't it? He saw that an open and beneficial information network wouldn't just happen by accident. It would require conscious effort, cooperation, a shared vision. He understood that technology could be used for good or bad, and that the choices we make today will determine the kind of future we create. It's a powerful message, and one that we should all consider.
Absolutely. So as we wrap up this deep dive, what are some of the key takeaways for you? What really stood out?
For me, it's how interconnected all these periods are. We started with mechanical automation, and that led to electronic computing. Then came the stored program concept, which made interactive computing and time-sharing possible. And those innovations, they paved the way for networked computing and the personal computer revolution. It's this remarkable chain of interconnected events.
It's a fascinating journey, isn't it?
It is, and seeing how social and cultural factors played a role in all of this is really interesting, too. It's not just about the technology itself, it's about how people use it and how it impacts their lives.
And for me, the aha moments came from seeing how early visionaries, like Licklider and Bush, anticipated so much of what we take for granted today. It reminds us that even seemingly far-fetched ideas can become reality if we're bold enough to imagine them. And the unexpected social impacts of these early technologies, like the online communities that sprang up around Project Mammy, they're a reminder that the future is often shaped by forces we can't fully predict.
Absolutely. The future is not set in stone.
So here's a final question for you to ponder. Given this incredible history, what decisions do we need to make today to ensure that our current technological advancements lead to a better future, a more open, equitable, and beneficial future for everyone? And what role do you, as an individual, see yourself playing in shaping that future? Think about that.